Thank you. I just want to make sure that this is the correct talk giving, but I think that's a good indication, right? So that's probably correct. So I apologize for inconvenience caused by my being backwardish in technology, right? And moreover, the internet decided this afternoon to stop working my computer or something. So in any way, I want to thank the organizers for, of course, for inviting me to this wonderful program and for giving an opportunity to talk. This is, in fact, sort of you can consider as an introduction to Marco's talk that was yesterday, backway introduction. And so what I will be talking about, I will try to connect what Marco was talking with the theory of solid spectral theory of soliton gases. So this is joint work with Marco, and I will start with the nonlinear dispersion relation for focusing nonlinear Schrödinger equation. Even so, you may have seen these equations before. So Z is a complex variable, gamma is some compact in the upper half plane, and I'm sure I will need some. Something. Yeah. So I have. So if that is so gamma is some, I don't know, some curves plus, and full gamma will be gamma plus union complex conjugate. And so the first equation is, as you see, it's an integral equation, Fred-Coulomb integral equation of the whatever type. It depends of this spectral scaling function sigma of Z, which is assumed is non-negative and continuous, so having some nice properties. So the first equation has a known function U that defines the density of space. In the language of Marco, that was the measure that we were finding on this contours, and it was called rho, I believe. And this lambda is a reference measure, which is either arc length or the area measure in the case of one-dimensional or two-dimensional compact gamma class. Okay, it's pretty abstract so far, but you can think gamma plus is something, the collection of this curve. So when we consider integral equation, so the U is the U that we are interested in is density of states, right? When many of you have heard already, and the second function is density of fluxes. And if we have this, right, let's also note for ourselves that this specific kernel is a Green's kernel for the upper half plane. So therefore, this quantity I will call G of U the lambda and the G of V the just a notation that will be used. So what can we? So how can we possibly observe anything related with these quantities in numerical experiments or maybe even in real experiments? So there are, of course, many observables when it comes to solid and gas that we can derive from this equation. Let's talk about the simplest one. If we take this function, a known function V and a known function U, and divide one by the other, let's call it S, and we interpret it as the effective speed of element of the soliton gas, which is earmarked by Z, right? So then it's very easy exercise, and like I've done it many times in my head, as you can do also. Probably just multiply the first equation by what? By the first equation by S of Z. Multiply through and subtract the two. If you do that, then you will find for a known function S, you will find this equation that is known as equation of state. for the focusing NLS soliton gas. And so what this equation of states, what does it express? It expresses this now unknown function s of z, the effective speed. It expressed through the density of states, if you know density of states, right? So that express this. So now the equation has a very nice structure, so you can see it this way. So by the theorem S0 as a result of our calculation, the theorem S0 will turn to disaster, right? Will be 4 times real part of Z. And so you can think about it. If U is equal to 0, so there is no density of state. There is just vacuum or something. And then so the speed of the soliton is just S0. It's the speed of the soliton in vacuum. There is no interaction of anything. Our earmarked soliton earmarked by Z with anything else. So it's just S0. But if the density of state is non-trivial, so this U has some positive function, at least somewhere, U of W. Then there is a correction to this speed in the vacuum, and that sort of equation was first found by Vladimir Zakharov in 78 paper, where he considered the rarified soliton gas, which was not, of course, called soliton gas at that time, but rarified collection of many solitons on the real axis. And so here, instead of making it an integral equation in Zakharov's paper, here is S of Z is approximated by its leading order behavior as 0. So that is just a formula for modification of the speed of a soliton in the rarefied gas. And then the very fundamental contribution of Gennady was that Gennady made connection from rarefied, what we call now rarefied gas to dense gas, where here is indeed S. So it turned into integral equation. Okay, so that's next slide I will maybe show some illustration of that, but just to complete the picture, I would say that right now we assume that the gas is uniformly distributed in space-time. So any x, any t you choose, you will see the same spectral picture. But if there is some dependence, maybe a slow dependence on this x and t variables, and so then we consider all the quantities here also dependent on x and t, although very slow, then we will have additional equations here, and the collection of two, Gennady in his 2003 paper, Gennady called the kinetic equation for soliton gas. It was for KdV soliton gas, but now we have it for focusing NLS soliton. Okay, so if you want, for whatever reason, you want to consider KdV soliton gas, simply replace minus Z bar with Z. And instead of considering gamma in the complex plane, put gamma on the real axis, right? And you will have the soliton gas for KdV. So that's illustration of what I was trying to tell from this 2016 papers. Perhaps you've seen it many times. So there is let's interpret this wave as a gas, and then there is a trial soliton here, and we consider two types of evolution of this tall soliton. One is a free evolution, then in a given amount of time, soliton will be here. But another is this is as if there is no interaction at all. It's soliton in the vacuum. But if this soliton runs in the real gas, so each interaction will give a little bit phase shift forward, and therefore, in the same amount of time, instead of being here, the soliton can be found here, right? So that's why I refer it to observable, what you can extract from these two nonlinear dispersion relations from the previous one. So today in this talk, I will try to connect developing theory or developing story about spectral theory of soliton gases, I will try to connect it with algebraic geometry, potential theory, geometric function theory, and whatever else I can find, right, so far. Okay, so, but let me first give example again. Example is solution of these two equations of these two nonlinear dispersion relations that I showed in the very first slide, right? So the solution. So first, if we have gamma, just a vertical branch cut from minus IQ to IQ, right? And take sigma equal to 0. Sigma equal to 0 corresponds to what we call condensate. And you will see in shortly what meaning it has if you consider some type of energy for soliton gas. So we consider condensate, so sigma equals to 0, and this is our gamma. Then it's very easy to see that this is a solution of the first equation, and solution of the second equation will be just 0, because it's a vertical segment. So all the speed of every soliton is in this case 0. So therefore, even if you have very many of them, it's still 0, and so V equals 0 solves the equation. You can see. Okay, so now I will try not to talk. I will try to cover as much as I could, but nevertheless, please feel free to ask ask questions. So the second example, when we don't, and that is called bound state condensate, because all the points of spectra are have the same real part. Now let's consider this arc of a circle as another example. So let's loosely call the circular condensate, because it's a 0, and that's arc of a circle of a certain radius. And then we can again solve it. In the recent paper with Fudong 1, we solved it not for one arc, but for many arcs on the circle. Again, it's possible to construct explicit solution. But let's here stay with one. So then we can again solve for U, and eta here is the same as my spectral variable Z. Sometimes it's eta, sometimes it's Z. I apologize for that. So you see this eta 1 gives you the location of that point, end of the arc, and B is a cosine of B is a cosine of B1 is a cosine of X. Okay, so now if we consider particular case of this condensate, so it will be full circle up to here. Right, in the upper half plane and in the lower half plane, it is the same thing. Then this formulae becomes particularly simple. This is the imaginary part of eta, imaginary part of eta squared, normalized. And if you look at the effective speed, you will find that it is -8. If you divide one by the other, you will get -8 real of eta, which is incidentally double speed of a free soliton. So for some still unknown to me reason, this configuration of soliton gas doubles the speed of any element of the gas compared to the free solid. Okay, so let's look at let's now talk a little bit about solution of these integral equations. These integral equations are, as I said, a little bit tough, because if you consider them as Fredholm integral equation, it's not clear what type it is. If sigma is positive everywhere, it's type 2. If sigma is identically 0, is type 1. If sigma is switching 0, non-zero, is sometimes called type 3, which is what? Everything else. Yeah, everything else, which I never heard before until I faced this problem, and very little is known about that solution of this equation. So therefore, let's again consider simple case when sigma is 0, right? Condensate. So then this equation in the notations that I introduced can be written this way: Green's potential of some unknown measure mu, where this measure mu is u times the lambda, so we don't know this measure, equals the right-hand side, which I define fine. Okay, so we have this equation, and well, for this equation, it is well known that it is Euler Lagrange equation, a variational equation for the Green's energy functional from classical. It is a classical subject of potential theory. For example, look at the book of Saf and Totic, where quite a few things are known. So, namely, if we introduce this this energy, J, I for some reason I put J0. We'll see why it's J0, right?
So you integrated with special values in the
What?
in the formula term. So Green's function has log certain time. So you're integrating.
I'm multiplying, so in respect, yeah, it's double integral. So G already has one integral, so that's a double integral. So it's usual weighted logarithmic energy.
It's G of mu is the default first term.
Yeah, it's G of mu. Okay. And so we can consider this energy, and we can ask the following question. We would like to minimize, let's say, this energy weighted it is Green's energy to be exact. Weighted Green's energy, we want to minimize it with respect to positive Borel measures with support on gamma plus. And then it is well known that at least in the conditions which you normally assume on the contour and on the right hand side, that solution that minimizing measure exists and is unique. So solution exists and is unique within reasonable assumptions about these equations, and I wouldn't go into specifics now, which are reasonable. Okay, so now how can we approach general case when this is not a first Fred-Golomb equation of type 1, but with a general signal? So the approach was suggested in my paper was Arno Pullars in 21, where obviously the energy functional needs to be modified because of the extra theorem. And this is the modification. So this extra theorem takes J0 from before, add this extra theorem, and and the new energy is equal to the sum when this expression is absolutely continuous with respect to measure lambda and plus infinity otherwise. So that's how we define it. Okay, and by the way, if I go back, it's yes.
How does the var phi thing come into that formula?
How what?
It says for a continuous var phi gamma plus to r we define.
For a continuous, yes.
Where's that var phi?
Var phi, maybe it's so var phi is supposed to be that. So all phi's are the same, var or not var. It doesn't matter. For the, I'm sorry for the typo. So this by the way, this logarithmic energy and the solution of this minimization problem has a nice electrostatic representation, which basically, and again, I'm skipping the fact that I'm talking about Green's energy, which is basically you have an external field phi, and you have a conductor which has form gamma. So find the distribution of a given charge in this external field. But then, what is the meaning of this term from this electrostatic representation? I don't know physics enough to tell what can be the meaning of this extra term. But okay, we're at the yes.
Sorry, Alex, gamma plus is fixed, right?
It's here.
So it's a given, a particularly given.
At the moment it's fixed. Later, if I manage to get it, we'll start to be moving. That's what Marco was doing the last talk. He was just moving this gamma plus. Okay. And however, the theorem, and that's a little bit simplified version, says the following. So if we consider the set of zeros of this function, spectral scaling function sigma on the support, and if we assume that this is that it is thick at each point, and I don't want to go into details what is thick, but you can think that this set has no pathologies, right? And that there will be a little bit description later if this has happened. And also phi is positive, continuous, and superharmonic in the upper half on the contour, and superharmonic in the upper half plane. Then this equation calls for all points of gamma plus, and where mu is a unique minimizer of this energy 11. So in particular, it holds when the set S0 is empty, or it is a connected set that with more than one point, or a union of such sets. Right. So in this case, so in pretty good collection of situations, the theorem tells us that solution exists, and is unique. Also, it doesn't tell us how to construct it. Well, it minimizes the energy, and that the way you can construct. And by the way, the way is, so if omega is a bounded open set, the Dirichlet problem for the Laplace equation in omega has a continuous on omega closure solution for every continuous boundary condition on the omega, if and only if the omega is thick at all its points. So that a little bit explains the connection of solvability of the Dirichlet problem with this requirement of this topology of thick and thin points. So of course, to KdV, this because of the comments I made before, that is covers the KdV soliton gas as well. Okay, so now I want to discuss, so with that in mind, that for every sigma, every reasonable sigma, we have a minimizer. With this in mind, let's consider the following problem. We now fix the right-hand side phi and fix gamma plus. So that is fixed, and the right-hand side fixed. What is not fixed? Well, we can vary sigma. Sigma is allowed. Sigma is a spectral scaling function. It is non-negative. We can vary. And the question is, okay, so when we achieve the minimum, so now we vary sigma, right? When we achieve the minimum of the energy. And the simple consideration tells us that the condensate, which is J0. So 0 is this notation means that this is the minimizer for which sigma, right? So the solution, the density of state for the condensate is less or equal than the density of state for any other gas with the same gamma and right hand side, right? That's what this inequality. Test, right? And the reason is very simple. So you consider this energy for condensate, and it is minimized at the mu zero, and then you take some minimizer for non-zero sigma, right? You call it this, and because this is the minimizer of G0, obviously you have this inequality, right? But then you want to compare these two, and because the energy for sigma contains extra positive term, right? This one. So obviously this inequality also holds, and therefore we have the statement that the condensate minimizes the energy when you fix gamma plus and you fix the right hand side. Okay, so let's now try to interpret what does it mean, right? So we consider this. So we take some sigma, right, and consider this energy, and it consists of this three terms as it was defined. That was J0, and that is this extra term, and then we can combine the integrals, and we get this expression. And please notice that the equation, that the variational equation, what was the Green's energy plus sigma u equals phi, right? And here we subtract 2 phi. So if we take one negative phi away, that should be 0. And so what we end up with this expression. Okay, so that's nice. So we calculated sort of this energy we found this expression. But then if we consider first nonlinear distortion relation, then this phi is imaginary part of Z. So therefore, and we know that the average intensity of the gas is given by this formula, right? Which is exactly this with the opposite sign. So the energy that we considered when we were minimizing the problem for the first NDR equation is in fact negative average intensity of the soliton. Yes.
So I just wanted to clarify, so the term you added in the to the J0 was like integral of sigma times u squared.
Right.
But then u is
This
related
one.
to mu explicitly, is that right?
Yeah, U is the density of mu. U is the density of this measure, of this minimizing measure.
Given or no? I mean, when you
No, it's the meaning of U is that this is the density of this measure. In that sense. If the density doesn't exist, it's we assume that this wasn't it.
So hang on, so you have a measure mu whose density is u, is that what you're saying?
Well, what I'm saying is that when we find the minimizer, right, its density is U.
Yeah.
Okay, so now I want to say, start connecting to what, and I know time goes fast. So I try to connect with what Marco was talking about in the previous lecture. So let me briefly let me try to briefly start with the finite gap solution for NLS. When we consider, so soliton gas can be thought of as a collection of many solitons, an increasing number of solitons, or it can be thought as the finite gap solution of focusing on linear Schrödinger equation with a with a high genus, right? Many bands. And so the process then, when we increase, so what corresponds to the increasing of number of solitons, increasing a number of bands, and simultaneously shrinking them in a certain way, the size of each band. So that is then we can think about hyperelliptic Riemann surface with A and B cycles as followed, and so on that Riemann surface. And this choice of A and B cycles, as shown before, right? We can consider uniquely defined differentials dPn, dQn. N is 2n is a genus of the surface in question, and they are uniquely defined. How are they uniquely defined? They have only one pole at infinity on each sheet, and the behavior is as described, and also they are real normals. That's a unique way to define them. And as Marco discussed last class, then the corresponding finite gap solution can be written in this form. Here there are two of these differentials, and that function that is bounded on x. We don't consider we take t equals 0 for now, but for all x's, this function is bounded. And so then the Harashevach spectrum will be just the curve where imaginary part of this quasimomenta function is 0, right? Then it will be bound. Okay, so with this said, we consider this A and B periods of this differential Pn and Qn, denote them non-tilted and tilted quantity, and then we say, okay, we have this many periods of these differentials. Can we find some equations that connect them? And of course, these equations are very well known, and these are Riemann bilinear relations, which read for two, let's say, meromorphic differentials written here. So where f and g are some differentials, and particularly we can take as dg, we can take dpn or dqn, I'm sorry, n is absent. And for the other one, we can take any of the normalized holomorphic differentials for this Riemann surface that can be written in this way. And so this R is this radical where here is all branch points, and the polynomial here is such that this condition is satisfied. So this is Kronecker density. Okay, so everything is uniquely defined. So what we have a system of linear equations for this. So one system for wave numbers, the other system for frequencies. They are separate, and they called nonlinear dispersion relation because they are connected with each other through the underlying Riemann surface. Okay, so oops, I pressed something wrong. So okay, so we have this, and so you can calculate. You can easily figure out that the number of unknowns equal to the number of equations. So we have a pretty decent chance to solve it. And moreover, so let's make also two observations. First of all, the differentials are real normalized. So that means that our unknowns are real. So if we take imaginary, therefore we can take real and imaginary part of these equations, and they will block triangularize by doing so. And number two is that also the matrix that we have here, the coefficient matrix, is a Riemann period matrix. And because Riemann period matrix is non-singular, we have every chance to prove existence of solution. So we separate this equation, imaginary part, real part, and then we play the process of taking thermodynamic limits, so that means increased dimension of this system, because once you solve this system for k and for wave numbers and for frequencies, so the other tilted quantities will follow just more or less for free. It's block triangularization of the system. Okay, so again, I'm skipping details, but the question is what happens in the large n limit. And so in the large n limit, we will in some cases we can prove it with error estimates. In other, we cannot still prove it with error estimate, but we will come with this nonlinear dispersion relation for that one. Okay, so we have this nonlinear dispersion relation, and so we have some function in the process. So this function U tilde, V tilde, they interpolate this wave numbers and periods, scaled wave numbers and periods. A function var phi is the normalized density of the center of bands. Or you can think, if you want to think it as a soliton, then it will be the density of solitons. And nu is gives you this scaled logarithmic scaled band of each band. Okay, so very good. So now what we want to discuss. Of course, natural question is. What is the object that gives you limit of this Riemann surface, weird Riemann surface, where you have more and more bands of shrinking size that accumulate? Unfortunately, I cannot answer that question. I don't know what it will be. But then there is, okay, so then there is the next question. So what will be the limit of this quasimomentum differential? Which I take its expansion at infinity. That question I can answer. In a sense, what is nature to consider as a limit of the sequence of quasimomentum differentials? And the answer goes, as is again our paper with Foudon 1. So we decided to take large n limits of each coefficient here. And then, and it happens to be this large n limit happens to be this expression. When n is 1, you already seen it at the second slide, where I told that the energy in the minimization problem is average minus average intensity, right? So I use this formula. It's a reference measure. If it is a contour, it's arcness. If it is, yeah. And so we therefore, when we consider soliton gas, we have this density of state U of z, and then we define coefficients Im in this way, and then form this expression and call it the thermodynamic limit of quasimomentum differential. Okay, fine. Okay, and so what is next? And then, if that is the case, we can actually calculate the expression for this quantity, for this limiting differential. It will be just 1 plus Cauchy transform of density of states that is tweaked according to the angle of the curve gamma that you follow, right? That is the expression. So that immediately tells us that this object is analytic everywhere in the complex plane except on the point of gamma. Now gamma is gamma plus and Schwarz symmetrical. And also, okay, that's great. And also we can easily find what happens, the jump over the contour, which is obvious. This check or brief means this tweak thing. And also we can find the average. And the average will be 1 minus finite Hilbert with some coefficient finite Hilbert transform of this object. So this the differential connects the somehow connects the to the, it is constructed through the density of states, and if you know this object, you can express density of states. Okay, very good. So what I am saying that this differential is the generalized quasimomentum differential that from Markov, from talk of Markov. So maybe I shouldn't drag you too much through the calculation, but I sort of take antiderivative of this differential dp dz. Well, not of the differential. So the function 2gx of z will be its derivative is that. And the reason it's called 2gx, people who were in business working with G function, it's a remnant of the fact that this is x derivative of the G function that you calculate doing semi-classical. For example, asymptotics of focusing nonlinear Schrödinger equation, and so once we have expression for dp dz through the Cauchy transform, we can calculate now the antiderivative. We can calculate the average. We'll get this expression in particular, the average over the jump. And we can compare this average obtained over the jump. We can contain with the other equation from our paper with Gennady. And so what is that? That is a full nonlinear, full first nonlinear dispersion relation. So what I mean, what we usually talk dispersion relation. Remember, we have this system of linear equation that was split into real and imaginary part. So usually we were talking about imaginary part, but if it take full system of linear equation and go to the limit, then oops. And go to the limit, then we will get this equation. So if we can compare these two, we will immediately see that in terms of the density of states and the spectral function sigma, and also the other function that gives you density of state for carrier density of state, right? Because there were A cycles and B cycles over there. One was tilted, another was not tilted. So we will get this expression. Okay. So now we are considering condensate, right? Now let's go to connect with Marka talk. We were talking about condensate. So condensate means sigma equals 0. So this part is not existent. And so okay. So let's have this in mind. And now I will take this function z minus 2 to g of z, which is this antiderivative of this limiting quasi-momentum differential, and that will be the generalized quasimomenta from talk of Markov, and I will separate real and imaginary pattern. Right. So now we are getting to where we were last talk, and so then the relation. Then the jump, the average on the jump will be simply that. And okay, so what I want to do now, I want to demonstrate that the average intensity is indeed the Dirichlet energy, where by Dirichlet energy of we understand so there is by Dirichlet energy, we understand this expression. So omega here is so here is gamma plus. Omega is complement of gamma plus in the upper half plane, right? So this quantity is called Dirichlet energy of the harmonic function in omega. And this calculation shows that I start with I start with the average intensity and using the Green's first identity, I can show that this is equal to Dirichlet energy. Okay, and so minimizing the average. So we are interested in the following problem now. So what was the okay.
Reason.
Yes, there should be some reasons. Yeah, so we were talking last talk presented by Marka was something like that. You were given a collection of points in the upper half plane, and you can connect them, and then hyperelliptic Riemann surface. Thank you. Build on these points where these are moduli of the surface. And what should be connection that makes the energy the smallest, right? That's one of the formulation of the problem. Okay, so. Right, for example, this way, it should be Schwarz symmetric, right? Or maybe some other configuration gives us so that is the picture. So that I'm now connecting to the previous talk. So on this picture here, you see the set set gamma plus, right? And shown by blue, and gamma plus are zero level curves of this harmonic function v of z. It is harmonic outside gamma plus, harmonic outside gamma plus, and then there are and then there are other curves. And these are some other level curves of this function, but then there are also level curves of harmonic conjugate, which are orthogonal trajectories to the level curves of V. And so we call and we call it, so if you take, for example, this point here on gamma plus, so there are so almost everywhere on gamma plus, there are two orthogonal trajectories, one going to the left, one going to the right, in this picture. So we say that the curve has as property if the normal derivatives of V in both directions on the curve are equal to each other. Otherwise, if we don't have as property, we have some mismatch. So some normal derivative is bigger than the other, and we call the dominant direction. The direction, so we take this point, so say this normal derivative is bigger than the right normal derivative is bigger than the left, so the dominant direction is right, therefore, and the left is recessive. If they are equal, you can choose as you like. You can assign as you like, dominant and recessive. Of course, it makes some sense to preserve some continuum. Okay, so that's where we define this these ideas, and now let's say that we start with some collection of points B1, Bg in the upper half plane, and we consider that the second kind differential, it should be D. I'm sorry, it's not delta, it's D. Where P is this differential is unique. It's a quasimomentum differential for the Riemann surface based on this, point. But it may happen that and then we are looking, of course, on the and with this quasimomentum differential, we can associate quadratic differential. Right, Q equals dp squared, and then we can talk about trajectories of the quadratic differential, or we can talk about the zero level curves of imaginary part of this function p of z. It is the same, and so what that can be? Well, that is so the point is that. These are, if we're talking about this differential, it will have the described here, and we can consider the zero level curve of this function. It will this collection of curves will have S property, derivative to the right and derivative to the left of imaginary part will be the same. Okay. Okay, that's good to know, but what can happen then, for example, if you have configuration like that, this, and that. I suppose you have this configuration. And then you tweak, so 3 points and Schwarz symmetrical, and then you start tweaking the parameters. It may happen that in the process, you will get this picture. Right, so what that means, of course, that that zero of the numerator, right, becomes one of the values in the denominator, and then you have a square root in the numerator instead of denominator. So therefore, we consider that. Okay, so therefore we consider the set.
E was the last point in the previous slide.
Where?
Not this slide.
Yeah. Yeah. So we consider this set E, which consists of poles of this object, right? So not zeros of order square root, but really poles. So this set is basically a subset of the B of BJ's, and the number E of such points is in general less than G. Okay, so we have this set E, and now we define the class KE of compacts in upper half plane that actually in closed upper half plane that have.
Can you say a bit more?
What's your question? Okay, and so we now consider the class of compacts. What compacts do we consider? Well, first of all, it should contain all points E. That's number one. And number two, there should be no point of E that is hanging like that. So every point should be connected either to real axis or maybe to another point from this set. Right, so this set of this class of compacts we consider, and then we define okay, and so for a given set E, and then a hyperelliptic Riemann surface built on this, we denote by F the collection of branch cuts of RE. So the collection of smooth arcs connecting these points E and E bar, right? So pretty much as I was showing. It doesn't have to have any special property. Just make sure. So for any of this, for example, this picture doesn't work. This picture works, right? This, so we have 3 points. This picture also can work if this is such, let me think, right? So this picture work, this picture work. This picture work if we insist that E is from our collection, right? Then this is also allowed. And then we should we take any other compact from this set. So and we say that if we take compact from the set, we said that it has Jenkins intersection property with respect to this collection of curves F, if every dominant orthogonal trajectory, almost every. Right, dominant orthogonal trajectory on our set F intersects with K, right? So in other words, right? So you suppose so this is, let's say this is our F, and then you make some compact, I don't know, some set somewhere, and if so one direction is dominant, the other direction is not dominant. So if every dominant orthogonal trajectory, almost every intersects with this set K, then we say that this compact K has S property with respect to F. And then the theorem said that if a compact K has Jenkins intersection property with respect to F, then the average intensity of F should be less or equal than the average intensity of K. By average intensity, of course, I mean the average intensity of a soliton gas that is built on the contour F and on the compact K. Right, which may be a contour or maybe 2-dimensional set. And moreover, the equality holds if and only if they are equal up to measure 0. So, okay, so that is what was the main theorem of yesterday talks of Marka, and then some. So what consequences we can? So I'm sort of getting to the end of my talk. Yes, Ken.
Is that measure 0 set in 2 dimensions or in 1 dimension?
It's a good question because measure 0 with respect to F, and F is 1 dimension.
Okay.
Okay, the question is good. Okay, and so So now let's try to use this theory. So if we take this collection of contours F within this class, of course, and we start to moving it. We start to move, so the branch points are fixed, but the contours we can move. And in which direction to move, right? At every point, we have, let's say, one recessive direction, one dominant direction and one recessive. So we move it in dominant
No,
direction.
recessive. You want to decrease the energy. Okay,
No, I want to, the other guy should have more energy. So I'm moving it in this. Yeah.
Just a question following, it's related to what you're asking. I think the inequality is wrong.
Which one?
The flip side. So you want to maximize the energy and not minimize it.
No,
no,
we
that's a
want-
different energy.
it's a different, there were many problems.
No, I know.
Here we want to minimize.
Okay, but you were.
Here we want to
Minimize.
Yes, okay.
So if we have, suppose this is our contour, let's take simple situation, this is our contour F, and let's say to the right is a dominant direction, right? So if we deform it this way, right? So then every dominant trajectory from here will intercept the deformed contour, and therefore the energy, this energy will be less than
Yeah.
that.
Right.
Okay.
Okay, but you want to minimize the energy, so if you go in the other direction.
Right, yeah, that is true, but all that I said, that if you move
Oh,
it
yes.
in the dominant direction, energy is increased. And if you move in the other direction, energy is, will decrease. Of course, I'm talking about small deformation. So what does it mean small? Small, that the smooth displacement, as well as small variation in the normal direction. So the normal derivatives would not be affected too much. And in fact, these deformations do not have to be small as long as dominant property is still there and connectivity, you don't change connectivity of the points. So which connection belongs to the same connected component is not changed. And also this argument show that any F with, so if F happen to have S property, it may also happen, right? It's a special curve, for example, it's the this zero level curves of associated with quasimomentum differential, right? So it is a local minimum for sure, right? And moreover, in certain cases we can claim that this is a global minimum as well. And in particular, if we consider subclass in KE with the same connectivity as F, then it must be in this subclass it must be a global. Okay, so what other classes? So I don't know. When should I
Maybe-
stop?
So this is roughly an hour since you started, so if you can wrap up.
Yeah, that's what I'm doing the last half an hour trying to.
You can still take another half hour.
Few minutes. Okay. So let's consider some other classes. So one subclass is hiding here. It is a subclass M. So if I take my curve F that I was talking about, so given an S curve F, the class M consists of all compacts that have the same or larger connectivity between points than F. So so that means if two points are connected by contour F, they have to be connected by any element of this of this class. And also consider another subclass, which consists of all possible Schwarz symmetrical branch cuts for the hyperelliptic Riemann surface based on the set E and E bar. So, and the corollary says that the energy that this F minimize the energy in this class. That's part A, and part B says that there is a unique minimizer in class L, and that is nothing else than the Harashabat spectrum of this Riemann surface. And with that, I want to point out that one question is still open, and that is what is a minimizer in this class, in the most wide class that I described. We have some ideas, but it's still in the process. And with this said, I want to mention that is very much seems to be very much connected with the classical, and that is next to last slide, with a classical problem of a well-known problem of Nikolai Chebotarev. So which says to consider complex plane and the set of points there, and we need to find the class and consider the class of connected compact sets K that connected, right? So it should be connected that should contain E. And the problem is to find the set K0 in this class with minimal logarithmic capacity, right? So minimal of logarithmic capacity one can interpret as minimum of logarithmic energy, and our energy with a total mass 1 in this setting, normalized. So the difference of this problem with what we are considering, and Marta actually talked about this at the very end of his talk. The difference is that the total mass is not fixed in our case, and the energy is not logarithmic energy, but Dirichlet energy, and then there is the external field also. So that's more or less the difference. But exactly this extension of the Chebotarev question, that was the last result that Marta mentioned in his talk. And so what remains is to break this requirement of connected compact, allow it to have several components, and that's how within this class, how the minimization, what is the minimum if it exists, and how many different minimum we can have. Certainly we can have several minimum in this case. That's what under consideration. Thank you very much.
I wanted to just to mention that as a comment on the last thing of the Chebotarev problem, even for the classical setting, it's not settled. It's not exactly known what happens if you require different connectivities. How this the only answer that exists is exactly for this problem.
And the answer is from certainty of 20.
Yeah, more or less.
Could you go back to your, the theorem with the inequality? Just want to make sure I don't understand something about it. So is there an assumption on what kind of set F is?
Well,
Is this a completely general inequality, or? do you
no,
need
F
the-
is here, F is where it says. F should be, and let F denote a collection of branch cuts of the Riemann surface with endpoints E. So a collection of smooth, or you can think piecewise smooth, but maybe smooth is enough, arcs connecting these points. And so that each point emanates odd number of arcs in the complex plane.
So it doesn't have to be the
As property.
No, I was wondering if I thought yesterday in Marco's talk, I misunderstood that, I guess, that for this theorem to be true, that F should be the spectrum of a finite gap.
No, spell is even stronger. For spectrum.
Here's a bit of notation clash, because this F is not the same as my F, right?
In this setting, but it's described that this F denote it doesn't have to be Zakharov-Shabbat spectrum. It even doesn't have to be S-curve, which may not be a Zakharov-Shabbat.
So when I wrote F, I meant the Zakharov-Shabbat spectrum,
Yeah,
so
and
that would be.
since you said
the
that,
minimizer.
that F is the minimizer, then I guess I'm also having the same, doubt as Ken is expressing. the-
Yeah, but this F is in Alex is just an arbitrary set of cuts of curves. So it's not the same, it's not the
It's not a
same.
minimizer, it's a
Yeah.
comparison between
It's just-
two
That's
components.
what I meant.
One is this F and the other is whatever having the problem. There's no claim that this is a minimizer.
But implicitly, there is the claim that the minimizer is that one that we used yesterday, right?
It's a more general comparison.
More general.
Yeah, you just-
yeah.
Right,
Have a set of this type, anything which has the Jenkins property with
Yeah.
it
yeah,
is going to have a larger end.
yeah. So it teaches you how to minimize effectively. You have this stringy spaghetti that you move around.
Any further question?
This, I have a weird one. This won't make any sense, but I'm trying to, keep Alex
Yeah,
there.
yeah, don't.
Yeah, for the general NDR equations, is there some energy problem which directly determines kind of the
Generally, you mean complex. And
Yeah. and that it would determine kind of the mean behavior?
It's a good question. All I can say that I wish I know the answer, right? So because
Of the solution, of the potential, yeah. So some kind of.
what is it? You mean some real energy or it should be complex?
these NDRs, then you.
Then do you want the solution of the NLS?
Yeah.
Oh, okay.
It's like,
But okay, the point is that usually when people consider some rhythm equation, right, slowly modulate situation, people usually move branch points. Well, we know that the contours follow, roughly speaking.
Right.
But what if you fix, so it's hard edges form? Yeah, and you want only to move the contours, right? Something along this lines.
maybe another way of asking this, it's a vague question, but is for a given configurations, sort of the NDR equations, do you know what the space, the compacta should be, so that you phrase the variational problem and the solution actually gives you the support set?
I'm not sure I'm getting the question, because in so far in the setting of NDR, the support is given, this gamma plus is given. Be it a collection of a curve or maybe a two-dimensional compact or union of such, right? It's given. That's it, it's given. Now, one can ask, okay, for a given support, well, we're talking about content, right? So support, it's all information that we need for that. For a given support, we have the Dirichlet energy or average intensity, which is the same, right? And now we start playing with the support, trying to figure out when the Dirichlet energy is minimum, basically. So there are many games you can play. One of the games is that you fix endpoints, right, and allow to move contours, right, or allow to fatten them to become two-dimensional things, whatever you want. It's one game. You can design another game.
Right. Thank you very much, Alex.